Yeah, okay, let's start. So, hi everybody, welcome to Math 184. Yeah, let me first talk about some logistics of how the class is going to work. So, as you can see on the left of the screen, I'm going to have some kind of running text over here, which is supposed to represent a bunch of blackboards which I have written before but have not erased yet. So yeah, what's going to happen on the right is going to duplicate what's going to happen on the left, basically, some with some extra information like examples and stuff. And let me also try to explain. Well, first of all, the most important thing is the grading. So, as you know, we are in the middle of a pandemic, so the gradient is going to work as follows. There's going to be, the most important thing is that there's going to be no negative, there's going to be no curve, basically. Your performance, you're graded based on your performance and not based on the performance of your peers. And yeah, this is due in particular to the fact that people, it's easier to cheat on the midterms and the finals and stuff like that. So that's why people who don't cheat get upset when they are graded based on the curve. So there's going to be no curve, but that said, the grades are gonna. I expect the grades to be pretty good. If the grades are bad, then I'm gonna rescale the criteria to make the grades better. So yeah, I understand that it's a hard time for everybody. So I'd like to first of all I'd like to accommodate everybody. If you have any kind of problems with any pandemic related unit, like an extension for the homework, or even the midterms or finals, please do not hesitate to email me, and I will be very happy to accommodate everyone. So and also the lowest homework is going to be dropped. And another thing that's related to the pandemic is that there is an unusual distribution. Right? So the midterm is 20% of the grade, and the final is 30% of the grade, which is due to the fact that, again, these are basically just larger homeworks. So that's why usually they are about twice as, well, not twice, but maybe 1.5 times as important. But here we're gonna, and that's basically the official UCLA policy. Both of these things are, for the time of the pandemic, these are the official guidelines. And yeah, but the details of how to submit homework are pretty standard. So it's going to be due each Friday. So not this Friday, but starting the next Friday, there's going to be a homework which is due in class. Due, well, right before class on grade scope. So there's going to be, yeah, you're going to get an email about the grade scope and all that stuff. And yeah, so you are allowed to write them up by hand or to use LaTeX. That's preferable. But if you do write them up by hand, then please please take good quality scans. Right? Do not take phone pictures with the blurry stuff, because yeah, David is here. David is going to grade your homeworks, and he's going to be very upset if he has to read your work for an hour. Oh, will the lectures be recorded? Yes, that's a good question. The lectures are going to be recorded. They are recorded right now. So I'm using some software for gamers, which helps me record myself, but and my voice and my screen, but not you guys. So please, and that was pretty hard to do, but the goal was to, okay, group me. All right. Yeah. Yeah. So there's a group me chat which you're you should feel free to use. Hold on, let me go back to the recording. Yeah, so I am recording myself, and the reason is that I want people to participate as much as you would like, without being shy and being worried that you're gonna end up on YouTube. So hopefully that doesn't happen. And yeah, so please, collaboration is encouraged for homeworks, but not for the midterms, nor the finals. So please use the GroupMe chat if you would like, but you have to write up the solutions by yourselves. Yeah, and another point about homeworks is that this is an advanced undergraduate class, which means that you're at all times you're expected to give rigorous justifications for your answers. No matter how silly the question sounds, like, is it always true? If it's always true, then you have to prove it. If it's not always true, then you have to give a counter example or some reasoning. So all your output, unless I explicitly ask for just the answer, all your output will be held up to a rigorous mathematical standard. Yeah, I guess that's okay. And there is one more piece of logistics, which is that I didn't announce because today is Monday, so I didn't want to confuse everybody. There's going to be no live lectures on Mondays. So every Monday there is going to be a pre-recorded lecture instead. Which may sound unusual to you, but so the reasoning behind this is that for some people it's more convenient to watch pre-recorded lectures when you can pause and fast forward. And for some people it's more convenient to watch lectures interactively. So I'm going to do both of these things, kind of mix them up and alternate. And during the live lectures, I'm going to try to be more accessible and try to interact with you and ask questions, and you're going to ask questions. But then for the pre-recorded lectures, I'm going to prepare to kind of, maybe some material is better suited for pre-recorded lectures because you can, sometimes I can just kind of explain a bunch of definitions without any trouble for an hour. So yeah, and you're going to get a separate email about that on Friday in case you forget. So yeah, there's it's not like I'm busy on Mondays or something like this. It's just that this seems to work better. And there's going to be I'm going to collect feedback at some point. If you hate it, then we're going to switch. And I think that's it. So for the logistics, any questions before we start talking about math? Okay. Yeah. Oh, by the way, since you're not being recorded, I encourage everybody to turn. I mean, if your circumstances allow, to turn on your video so that I could see a nice grid of faces, and I'd like to, when I explain things, I like to react based off your reactions. So if you look puzzled, then I'm going to explain more. But if you just nod a lot, then I'm going to speed up. So yeah. And yeah, please feel free to also use the chat for the questions, or to unmute yourself and ask a question if it's more elaborate. Okay. No questions. Let me move on and try to explain. So I'm gonna start with what I think is, I guess, the most important object in all of combinatorics, which is permutations. And so bijections and permutations. Oh, another point. I have prepared a poll because there is a whole bunch of prerequisites you're supposed to. Wait, there is no poll. Oh yeah, there's a poll. there's a whole bunch of prerequisites you're formally required to have, but then everybody has a different background. So what I'm going to do is I'm going to ask you to choose which of these you are just completely comfortable. You know the definitions, you can solve problems related to these objects. And this is anonymous, is just for my reference, so that I would know at the beginning whether I should go faster or slower. Okay, last call to vote. All right, sounds good. Let me save this. Yeah, so everybody knows proof by induction, but for the rest of the stuff, it's the opinions are different. Okay. All right, thanks. Now let me talk about bijections and permutations. So, by the way, we have a book, and I guess the way I'm gonna explain things is, oh yes, thank you. There is a book. It's this one over here. I put a link where you can download it for free if you are a UCLA student. So yeah, the book is it's more sort of, there's the problems in there are formulated in terms of live events, like where you go in a boat with some friends and then they fall into the water or something like this. So I'm going to try to focus more on the mathematical formulations, and you're encouraged to read the book and enjoy the descriptions of real life descriptions of the same problems. Okay, and in particular, I'd like to introduce some terminology right away. Namely, I'd like to define different kinds of maps. So let's say you have a map F between two sets, A and B. Then I'm going to say, then I'm going to call this map F an injection if f of A is not equal to f of A prime for any two different A and A prime inside your set A, the values are different. So you have your sets A and B. There is some elements in A and some elements in B, and the condition is that all these arrows have to have different endpoints. That's injection, and it's also usually, so I'm going to denote, sometimes I'm going to write, if it's an injection, I'm going to draw this hook arrow like this. Similarly, it's a surjection if it covers all elements of B. So if for each B in B there exists an A in A such that f of A is equal to B. So here I would draw A to be large and B to be small. The condition is that for each element in B there should be somebody in A that maps to it. And finally, finally there is bijections. F is a bijection if it is an injection and a surjection. An injection and a surjection. So in other words, I have your sets A and B, and f just maps each element of A to exactly to kind of a separate element of B. And each element of B is mapped to by exactly one element of A. So maybe I could also draw something like this, just to, yeah. And so for a surjection, I guess I'm not gonna do it very often, but it's a nice way to just memorize, to kind of represent them visually. A surjection is going to be denoted by this double head arrow, and a bijection is going to be, I'm just going to draw a little tilde over the arrow. So bijections are going to be the most important ones. And if you need an easy way to remember, because these are three similar words, then you can, injection, you kind of, injection is a good word for this concept, because you kind of inject, you have small set A and you inject it into big set B. That's the way I memorize it. And then surjection is the other possible option. Okay, and finally a permutation. So let me, another very common notation for me is going to be that I'm going to denote by bracket n the set of integers between 1 and n. So a permutation is a bijection f from the set from bracket n to itself. In other words, you have your integers 1, 2, all the way up to n, 1, 2, all the way up to n. Right, so, and then you kind of, if you have a bijection like this, then in other words, is just a way to order these n elements. So there is a permutation is basically you just take these n numbers and then you shuffle them in some way, and the list you get, all such possible lists are permutations. So I guess now I'd like to ask a question. So if you think even if you think the question is easy, please just write something in the chat so that it wouldn't be silent for 5 minutes. So question is, how many permutations of bracket n are there? Okay, and an exclamation point. Okay, yes, so the answer is, thank you to everybody who responded. The answer is n factorial, which is by definition just the product of 1, 2, all the way up to of integers between 1 and n. So for example, yeah, I guess there's one convention which we are going to work with, which is that 0 factorial just by definition is set to be equal to 1. The product over an empty set is always equal to 1. And then 1 factorial is equal to 1, 2 factorial is equal to 2, 3 factorial is 6, 4 factorial is 24, and then there's 720, and I guess that's the 5040. And yeah, I don't remember the 7 factorial one. Okay, so that's a nice number sequence. And so I was thinking, like, what would I do in the first lecture? And I decided to do something slightly entertaining, which doesn't quite. So what I'm about to explain is not going to be checked in the homework or during an exam. I just would like to tell you something that I find kind of cool, because so I do combinatorics for a living. I was choosing between different fields, like being a software engineer or something like that, and then eventually I decided to do combinatorics. So I guess I'd like to kind of just a little bit explain, maybe illustrate why did I make such a choice. So yeah, let me just tell you a yeah, I guess one more. Okay, this is not related to what I'm going to say, but right. Okay, so first of all, let me try to mention that the asymptotics of n factorial, and I'm just going to write down that for any positive, for any real number, a n factorial is bigger than a to the n for large n. So if n is large enough, then what's going to happen is that you're going to multiply 1, 2, all the way up to n. Right, that's n factorial. And if you compare it to a to the n, a times a times a times a, that's a to the n. Then what's going to happen is that if n is large enough, then a is going to be somewhere near the beginning, and all these numbers are going to be much larger than a. And even though the first few are going to be smaller, then it's kind of pretty an easy exercise to show that this product is going to dominate the a to the n, which is kind of, yeah, I guess the moral here is that n factorial grows very fast. We're used to thinking that the exponential function grows fast when we, especially during these times, we see exponentials a lot, but n factorial grows even faster, much faster. Yeah, so and there's you can write down an exact asymptotic formula called the Stirling formula, which I'm not going to explain until later, but yeah, I just want to mention that n factorial grows fast. And anyway, and now I'd like to take a detour and just try to tell you some nice things according to my own taste. So the detour is going to be about standard Young tableau, which so just by definition, it's a very simple thing. So first of all, you define. By the way, any questions on the n factorial? Any questions before I get too excited about standard Young tableau? Okay, no questions. All right. So, okay, the first thing I'm going to define is a Young diagram. So a Young diagram lambda is, and I'm going to be slightly non-rigorous in this section. In general, I plan to be very rigorous. So if I'm not being rigorous, please stop me and force me to, if I'm doing some hand waving, please force me to actually produce rigorous proofs, because that's what you're going to be expected to do in the homeworks and the midterms and the finals. But here, just for fun, let me just say that a Young diagram lambda is a collection. It's a collection of boxes, right? It's how many of absolute value of lambda? Just let me just denote by absolute value of lambda the number of boxes. Boxes which are top and left aligned in a corner like this. So you imagine that the gravity kind of pulls you in this direction, and so all of your boxes are gonna be stuck in this corner. Yeah, let me try to draw an actual Young diagram. So maybe I draw something like this. So that's an example of a Young diagram. where the number of boxes is, I guess this is 10 boxes. It's 14 boxes, right? So you just kind of align them all in this direction, and yeah, it's a very simple thing, and then a standard Young tableau. T is a filling of the boxes of lambda with integers 1, 2, all the way up to n, where n is the number of boxes. So you use each number exactly once. And the condition is that such that the numbers increase along rows and columns. So the procedure is very simple. So I start, the top left box has to be labeled by 1, and then I just increase the numbers, maybe 2, 3, 4, 5, 6, 7, 8. I'm just randomly filling the boxes of lambda with numbers between 1 and 14, increasing in this southeast direction. Yeah. And okay, so that's, and now let's try to count them. Right, so let f sub lambda be the number of standard Young tableau of shape lambda. So I'm taking all possible fillings of, so I fix the shape and I take all possible fillings. So let's see. Now I'm just going to try to, I'm going to ask you. So for example, if lambda is a single box, then there is, so if you have a single box, then you fill it in with a 1, and that's it. So f sub single box is equal to 1. And then if you look at two boxes, which may look like this or like this, then there's also basically a single way to fill them in, right? So f sub two vertical boxes is 1, and f sub two horizontal boxes is 1. And then for the next time, for the next round, maybe, so for n equals to 3, maybe you can help me. So what are going to be the numbers of Young tableau for these three possible Young diagrams? Okay, 1, 2, 1. Thank you. 1, 2, 1. Right. There's the 2 here comes from the fact that you can either put 1, 2, 3, or you can do 1, 2, 3. All right. Now, can we do n equals to 4? I'm going somewhere. I'm not just going to do this for the rest of the class. So if I'm trying to draw all possible Young diagrams, which is challenging. Okay, 1, 3, 3, 1. But there should be 5 numbers. Because there I have 5 Young diagrams. 1 3 2 3 1. Okay, thank you. Yes, that was fast. 1 3 2 3 1. Right. Again, which one should I do? Maybe I should do. Yeah. So if I take a 2 by 2 box, then there is 2 options like this, and that's why the answer is 2. All right, and I guess that's good enough. So now let me try to tell you, or maybe, yeah, if I ask you to find a pattern, like what is special about these numbers for each n. Let's say, so I have n equals to 1, n equals to 2, and n equals 3, and 4, and etc. And for each n, I get a bunch of numbers. So what is special about these numbers? And yeah, some of you probably know the answer from before, or maybe you don't. But and one idea would be to maybe take the sum of these numbers. Okay, so should I? Yeah, let me even make a table. So if I take the sum of the numbers, is going to be 1, 2, 4, what is it, 6, 8, 10, 10. Yeah, and well, the sum of the numbers is not actually, it's a nice number, but not as nice as what I'm going to do. So what I'm going to do is I'm going to take the sum of the squares, of these numbers, which, yeah, it's a very strange thing to do. So like 1 squared is equal to 1, and now 1 squared plus 1 squared is equal to 2, and now 1 squared plus 2 squared plus 1 squared is equal to 6. And what's the next one going to be? 24. Okay. Yeah. So and that's not just a coincidence. I'm not cheating in any way. So for each n, the result is going to be the sum of the squares is going to be n factorial, which okay, it's a theorem. So let me theorem for each n greater than or equal to 1. What am I doing? I'm taking the sum over all Young diagrams lambda with n boxes, and then I'm taking these squares of the numbers of standard Young tableaux, and I'm getting a factorial. So what is my point here? My point is that this happens all the time when you do research in combinatorics. Maybe you're doing some complicated, whatever, computing cohomology of some topological spaces, or doing some other stuff. Every once in a while you can count some objects or some dimensions or whatever, and so you count and you look at the numbers, and sometimes the numbers tell you a story. Like this is a tip of an iceberg, which you can notice by just counting numbers. So to me, and you can discover all kinds of unexpected relations to the same numbers appear in very different fields, and then you can kind of see the connections which you wouldn't be able to see without the counting. So one of the main points of enumerative combinatorics is for you to be comfortable with counting things. You can count more complicated things with, like, it's basically a toolbox for you to count. So and it's just, from my point of view, it's a bunch of very beautiful tricks which allow you to explore the universe, I would say. But of course, it's also useful if you decide to become a programmer, or I guess in financial mathematics as well. It depends on as an undergrad, you probably don't even know what you're going to do. But for example, let's say if you decide to be a software engineer, then having experience with counting all these things is gonna, let's say you know how to count these set partitions, then at some point you're gonna have to program some of these things like trees or maybe ordered set partitions or something like this. And then because you kind of, by counting them, you understand their underlying structure, and so then you can better, you're just going to be more efficient when trying to program these things. But anyway, let me tell you another theorem about these standard Young tableaux. Another theorem is that, and yeah, by the way, the explanation for this theorem, if you're curious, is that because, okay, what do I mean by an explanation? There is the right-hand side and the left-hand side. And each side counts some combinatorial objects. Right? And factorial counts permutations. And this stuff on the left counts pairs of some kind of pairs of standard Young tableaux of the same shape. So whenever you have two numbers which are equal to each other, you can ask if there is a bijection between the corresponding sets. And in fact, so yeah, one explanation is called the RSK algorithm, which is a beautiful construction which is actually used a lot in computer science, if you're interested. So yeah, you can just go to Wikipedia and read the corresponding page. But yeah, that's not going to be in the class. Yeah. So any questions before I tell you another theorem on these things? Okay. No questions. All right. So yeah, another theorem is, so far I only told you how to, well, what happens if you sum up the squares of these numbers, but maybe I should also tell you just what a formula for each individual number. So the question that I'm going to ask is that given lambda, how to find the number of standard Young tableaux of shape lambda. And so maybe, I don't know, if I draw some shape like this, how can you find without, I mean, you can start trying to see how many options you have, but by brute force is not going to take you very far. And so let me try to explain this real quick. So let's say you have a box B. Let B be a box of lambda. So maybe you have some box like this, that's B. Then let me define the hook. Define the hook denoted h sub lambda of B. Just by definition, it's 1 plus the number of boxes to the right. I guess, yeah, let me write boxes to the east of B plus the number of boxes to the south of B. So the boxes to the east of B look like this. So they have to be in the same row as B. And boxes to the south of B look like this. So in this particular case, the hook h lambda of B is equal to 1 plus 3 plus 2. It's equal to 6. Okay, is that, so for each you give me a box, then I give you the hook. Well, h sub lambda of B is basically the size of the, whenever you have a box, then it's the size of the hook, which just contains this box, and you extend the box all the way to the right and all the way down, and that's the hook. So I can even, let's say, draw the same Young diagram. Then I can just I can find all hooks of all boxes. So maybe 1, all these corners are going to have hooks 1, and then so the hooks are going to look like this. And this is going to be a 2, a 4, 3, 2, 4. Okay, this is a 6, and this is a 7. Okay. Okay, theorem. Theorem is that f sub lambda is equal to n factorial divided by the product over the boxes of lambda, basically n factorial divided by the product of all these hooks. So I'm not going to prove it, but let me try to check it in a few examples. So maybe if lambda is a 2 by 2 box, then the hooks are going to be 1, 2, 2, 3. So f sub lambda is going to be n factorial. N is 4. 4 factorial divided by 1 times 2 times 2 times 3. And 4 factorial is 1 times 2 times 3 times 4. So I can cancel things out. And I get 2, which is the correct answer. Right. We have already computed f sub 2 boxes over here. It was equal to 2. And yeah, you can check other small examples, but for this large example here, the answer is also, I think, going to be easy. F lambda is what is the number of boxes? I think it's 10. 1 times 2 times 3 times 4, 5, 6, 7, 8, 9, 10. And then you divide by the product of hooks. 2 times 2 times 3 times 4 times 4 times 6 times 7. And now I guess I have to cancel out a lot of things. Okay, the 8 cancels out with 2 times 4. 2 times 3 cancels out with 6. 4 and 4. Okay, so I guess my answer is 2 times 3 times, 2 times 3 also cancels with 6. Okay, my answer is 5 times 9 times 10, which is 450. That was very fast. I did not have to go through all 450 options. So, yeah, and by the way, this formula is called the hook length formula. Hook length formula. So yeah, I guess what I see in enumerative combinatorics is just beauty. I like beautiful mathematics, and yeah, I personally think that this formula is beautiful because it gives you an easy way to compute something that looks hard, and it has a deep relations to other areas of mathematics. So generally, I like to do something more sort of algebraic flavor, and yeah, this hook length formula, and especially this formula here. If you ever take a class on representation theory, let's say, you're going to see this formula in there as well. So yeah, that's just, and yeah, whenever I talk about we're going to talk about Catalan numbers or binomial coefficients. There's a lot of beautiful facts about them, which I guess is why I personally like enumerative combinatorics. But of course, yeah, for you it's going to be also useful whenever you need to count some stuff. Yeah. And any questions so far? Sure. Right, yes, there is. Thank you, that's a good question. So the question is there a connection with the group of permutations Sn? And in fact, so this fact, there is such a fact for any, if you consider representations of your finite group, then for any finite group there is a fact like this. So if you just, these count like these f lambdas are dimensions of irreducible representations, which you may or may not know about, and then they together somehow get glued together into a space whose dimension is the size of the group. So yeah, but this combinatorial explanation does not use the group structure of the group Sn. Yeah. I don't know if that answers the question. Okay, thanks. Any other questions or comments? All right. Okay. Yeah, then I guess this is a good place to start, even though we have a couple of minutes left. So next time on Wednesday, I'm gonna actually rigorously talk about things like the size of the union of two sets being equal to the sum of their sizes, and stuff like that. So yeah, I see you all on Wednesday. Have a nice rest of the day.